Hello friends, today we will discuss the concept of superelevation in railway tracks. It is also called the cant. As you know, whenever a body negotiates a horizontal curve or it moves on a horizontal curve, it experiences the centrifugal force. Same is the case with a road vehicle also, and same is the case with a train also, a railway vehicle also. So whenever a train negotiates a horizontal curve, it experiences a force which is called centrifugal force. And this force acts outside the center point of the curve, that is outside the curve. It is horizontal and outside the curve. To counteract the effect of the centrifugal force, the outer rail is slightly raised above the inner rail so that the centripetal force is introduced, and this component of the centripetal force will counterbalance the component of the centrifugal force. This figure shows when the outer rail is raised slightly above the inner rail. And this difference here is the cant, let us say E. Now here this gauge is taken from center line to center line of two rails, and that is why it is not the regular gauge but it is called the dynamic gauge. Dynamic gauge. Dynamic gauge is the track gauge plus width of the rail head, and this is 1750 millimeter for broad gauge and 1058 millimeter for meter gauge. Now in this position, let us say here is the center of gravity of the railway vehicle at O. So the weight of the train will act vertically downward, let us say W, and centrifugal force will be horizontal, let us say F. Now if you divide these two forces parallel to the track and perpendicular to the track, then these forces will be like this. Now this is the component of W. This angle will be alpha, same angle as here, and this will be W cos alpha, and a component which is parallel to the track will be W sin alpha. And similarly, this force F, the centrifugal force, can also be divided into two parts. One will be parallel to the track. This is also alpha, so this will be F cos alpha, and another will be F sin alpha. F sin alpha plus W cos alpha, their impact is to have the pressure on rails. F cos alpha should be completely balanced by W sin alpha, and that is the concept of superelevation, that there should not be any unbalanced force. So F cos alpha is W sin alpha, or you can say that tan alpha is F upon W. Now F is the centrifugal force, and centrifugal force is given by m v square upon r. If you put m, that is W upon G into V square upon R, and F upon W will be V square upon R into G. Now here this speed is in meter per second, this is in meter, and this is acceleration due to gravity. That is 9.8 meter per second square. So this is equal to tan alpha now. and tan alpha is E upon G, G dynamic gauge. Tan alpha is E upon G. And you can now write this equation that E is V square into G upon R into small g. That is superelevation in MKS unit. G, the gauge in millimeter or in centimeter, V in meter per second, R in meter, small g in meter per second square. Speed generally we take in kilometer per hour, and therefore if you convert this speed into kilometer per hour, put the value of g, then this equation will be V square into G upon 127 R. Now this is the equation to calculate the amount of superelevation required when a train moves at a speed V kilometer per hour. Remember, G is a dynamic gauge here, and unit of E is same as unit of G. If you keep this G in millimeter, it will be in millimeter. If you keep it in meter, you will get in meter. Now here the radius of the curve. In railways, a curve is generally designated by its degree. And degree and radius, they are interrelated. Degree of the curve is the angle subtended by a arc of 30.5 meter, 100 feet. And that is the radius of the curve. So degree of the curve is the angle subtended at the center by a circular arc of 100 feet or 30.5 meter. So if you write the equation for this, it will be 30.5 upon D equal to 2 pi r upon 360. You can rewrite it. So R will be 1750 upon D. That is the correlation between degree of the curve and radius of the curve. So 1 degree curve will have a radius of 1750 meter. That is, or 2 degree curve will have a radius of 875 meter. Now a train moving at speed V on a horizontal curve, which is provided with superelevation of E, will have no unbalanced force. Means the centrifugal force is completely balanced by the component of centripetal force or weight of the train. Now that is called the equilibrium speed. Equilibrium speed because the forces are in equilibrium state. Equilibrium speed on the track, and when the train moves at this speed, there will be no unbalanced force. Now if speed is more than equilibrium speed, if the speed of the train is more than equilibrium speed, then the component of centrifugal force will be larger, and therefore there will be thrust on the rail or discomfort to passengers. And similarly, if the speed is less than equilibrium speed, then there will be unnecessary tilt of the vehicle. The component of gravity will be larger than the required centrifugal force or required for balancing the centrifugal force. So in that case, there will always be a danger of overturning of the vehicle. So question is, what should be the equilibrium speed? The practice which were used earlier on Indian Railways was that when the speed, the maximum sanctioned speed on the track is 50 km per hour or more, then equilibrium speed will be 3/4 of sanctioned speed, or maximum speed. When maximum sanctioned speed is 50 km or more, then take 3/4 of that speed as the equilibrium speed with a minimum value of 50 km per hour. With a minimum value of 50 km per hour. What does it mean? It means if the maximum speed on a track is 60 km per hour, then 3/4 becomes 45. In that case, you should design the horizontal curve for an equilibrium speed of 50 km per hour. If it is less than, if speed is less than 50 km per hour, then take the equilibrium speed as the actual speed, no reduction in the speed. But this was an old concept. Now Indian Railways does not adopt this concept. Now this is left to the chief engineer, and chief engineer has to decide the equilibrium speed on a horizontal curve based on certain factors. What is the maximum gradient on the curve? What is the composition of the trains which are moving on the track, including the goods train? What is the speed of goods train? What are the number of stoppages? All these factors are considered by chief engineer, and for any track, the equilibrium speed for which the curve is to be designed is decided by the chief engineer. Now, according to this equation, the value of E will increase with the square of speed because G is constant, R is constant for a given track. So, E will be proportional to V square. So, if you keep on increasing speed on the track, requirement of superelevation will also increase. But it cannot be increased indefinitely because in that case, it will be very difficult for movement of the goods train, for slow moving trains. It will cause the tilt of the vehicle, and therefore Indian Railways has specified certain maximum values of superelevation also, and these maximum values are like this. On broad gauge line A, B and C, the maximum value of superelevation is 165 millimeter. And for lines D and E, its limit is 140 millimeter. For meter gauge, for all routes, it is 90 millimeter, and for narrow gauge, it is 65 millimeter. These are the upper limits of superelevation that can be provided on a track, and that is how you decide the maximum speed which can be taken on a horizontal curve based on the superelevation, maximum superelevation. Thumb rule is that the maximum amount of superelevation is 1/10 to 1/12 of the gauge, dynamic gauge. And this is based on various studies conducted in Europe. That what is the maximum permissible superelevation? It is 1/10 to 1/12 of the gauge, and same is adopted in India also. Now, as I told you, the actual speed of the train is never equal to the equilibrium speed. It is either higher than equilibrium speed or lower than equilibrium speed. And when the speed, actual speed is more than equilibrium speed, then the Cant provided is less than what is required for that particular speed. Similarly, if the speed is less than equilibrium speed, then Cant will be in excess. And that is how the concept of Cant deficiency and Cant excess comes into picture. Cant deficiency and Cant excess. Cant deficiency is CD and Cant excess is CE, and actual Cant is CA. Actual Cant provided on the track is denoted by CA. So CD is Cant deficiency. Cant required minus Cant provided. Actual Cant provided. That is Cant deficiency. What is the Cant required for a particular speed? Remember, this speed is now larger than equilibrium speed, design speed. And what the Cant has been provided for the equilibrium speed, the difference between these two is the Cant deficiency. And the effect of Cant deficiency is discomfort to passengers. Because here, the horizontal component of centrifugal force remains unbalanced. Or this centrifugal force, the horizontal component which is unbalanced of centrifugal force, will try to push the rail out, and that will have a major bearing on track maintenance, and therefore it is important to limit it, this Cant deficiency. The Cant deficiency on broad gauge lines, which is permissible on Indian railways, Cant deficiency is 75 millimeter. On all lines. On meter gauge line, it is 50 millimeter. On narrow gauge line, its value is 40 millimeter. What does it really mean? It means physically that if we have provided a Cant of, let us say, 45 millimeter on a track, actual Cant provided on a track is 45 millimeter. Then a speed which will require a Cant of 45 plus 75, that is 120 millimeter, can be maintained without much discomfort to the passengers and without increasing maintenance cost of the track. That is the meaning of the Cant deficiency. Actual Cant is 45 millimeter, Cant deficiency 75 millimeter, and therefore you can maintain a speed which will require a Cant of 45 plus 75 millimeter. Now, same is the case with Cant excess. Cant excess is when actual speed is less than equilibrium speed. In that case, the Cant provided is more than what is required at particular speed. Now, it is important because on the same track you have slow trains and you have fast trains also. And therefore, the Cant excess CE on broad gauge is same, that is 75 millimeter. Here it is permitted up to 65 millimeter. And on narrow gauge it is same, 40 millimeter. Now, here also the concept is same, that if a train is moving at a speed which is lower than design speed of the curve, then there will be excess of Cant. And when there is an excess of Cant, the centrifugal force will be lower than the centripetal force. So, component of gravity will be now unbalanced. W sine alpha will remain unbalanced. And the impact of this is the tilt of the vehicle. Now, if this tilt is in excess, then the center of gravity line may fall outside the base of the wheel, and that can create a situation of overturning of the vehicle. So, to safeguard, these upper limits are specified in Indian Railways. This concept of Cant deficiency is extremely important when you have diverting tracks. A branch line takes off from a main line. This is the main line and this is the branch line. Now, what basically it requires, if this is the point here, what it requires that for the main line, both these points must be at the same elevation. Even these 2 points must be the same elevation. But this track requires that the point A must be at higher elevation than point B. That is to take care of superelevation or centrifugal force. So for this track, 2 points should be the same level. For diverting track, this must be at higher level, this must be at higher level than this point. Now in this case, the advantage of Cant deficiency is taken. So even if you do not provide any Cant on the branch line, if you keep these 2 points the same level, because there is a crossing here, if you keep the 2 points the same, 2 rails on the same level, even then you can maintain a speed on the branch line which will require a Cant equal to 75 millimeter. That is Cant deficiency. So E will be 75 and you can calculate what should be the permissible limit on the branch line. That is the significance of Cant deficiency. Same is the case with the diverting tracks. When you have 2 tracks diverting in opposite directions, this track will require, let us say a B, this track will require that B should be higher, but this track requires that A should be higher, and therefore these two conflicting requirements cannot be met in one layout. Whatever Cant you provide on one track, that will become a negative Cant on the other track. Now this concept of negative Cant and how do we calculate the safe speed on a curve, we will discuss in the next session. Thank you very much for watching this video. Please subscribe to my channel and forward the link to your connections.